The purpose of this video is to explain the operation of a common emitter transistor amplifier circuit. Locktronics kits, as we can see in front of us, provide a modular solution to quickly and reliably connect components together. So for example, if we want to put a resistor in this position here, you connect the spring connectors between the metal pillars, and it provides a reliable and quick way of connecting components together. The function of this circuit is to amplify signals. So what do we mean by amplification? What we mean is we want a bigger amplitude of signal out of the circuit here than what we put into it here from the signal generator. Why do we want amplification? If we use the example of a mobile phone, the radio signal coming into a mobile phone will be varying in amplitude depending on physical location. So for example, inside a building, the amplitude of that radio signal received could be very, very small if reception is poor and we have walls in the way of signals and we don't get very good reception. If you're outside, walking about outside, out with a building, the amplitude of the radio signal that you're likely to receive when your mobile phone is likely to be quite a large amplitude. In that case, we don't necessarily need an amplifier circuit bolted onto the receiver part of your mobile phone. But if the signal is very small, we need to amplify that signal to a certain level so that the circuitry inside the mobile phone is capable of extracting text and video information. So to mimic the radio signal, we have a sinusoid signal coming out of a signal generator at 1 kHz frequency. We can also have triangle waves generated. We can also have square waves generated. In this case, we want a simple sinusoid signal to mimic a radio signal that a mobile phone would receive through the air. Top trace here is the signal going in, and what we can see is channel 1, the peak to peak, which is the amplitude from the positive to the negative peak. It's the size, the amplitude of the signal is 2 volts. The amplitude of the bigger signal is 9.5 volts peak to peak coming out. We can also see that the signals are inverted with respect to each other. So when we have a positive peak on the input signal, we have a negative peak coming out. That's just a function of how the common emitter amplifier is connected. But what we can see is what's coming out is approximately 5 times the amplitude of what's going in. So we can say that the gain of our circuit is the voltage coming out divided by the voltage coming in. In this case, it's just less than 5 voltage gain because we'll have 9.5 volts coming out. We have 2 volts going in. 9.5 divided by 2 gives you just less than 5. So that is the gain factor of our circuit. How is the gain determined by this circuit? So the answer is it's done in 2 ways. There is a current gain factor from this transistor component, which takes current into its base pin here. A transistor has 3 pins: base, emitter, collector. If you have microamps going into the base, 10 to the minus 6 amps going into the base, and you bias the transistor in the correct way, you can then have milliamps coming out of the collector pin. So you have a current gain in the order of more than 1,000. We don't want 1,000 current gain out of our circuit, so what we do is we use these 2 resistors to modify that gain to a set level. The current gain of each transistor will be slightly different through the manufacturing process, So we use these two resistors here to set the current gain of the circuit. We have two resistors here. We have 33K and a variable resistor here that's set to 4K7. The reason these resistor values are set like that is we need to have the base and emitter junction forward bias. What do we mean by forward biased? What we mean is base to emitter is a diode indicated by that arrow on the component symbol there, and that must be at least 0.6 of a volts to switch the transistor on into its linear mode. And if we do that by biasing with these two resistors, we set the transistor up in such a way that it's in its linear mode, and if we then put an AC signal going into the circuit, we can have AC amplification. So we have power gain in the AC world. You cannot have overall power gain from input to output. So this circuit needs to be powered by a DC power supply we have at the back. We have 15 volts going in here, such that, why do we need 15 volts? We need 15 volts to bias the base and emitter junction to the correct voltage so that the transistor is switched on and we get it into linear mode. If we get it into linear mode, we can have microamps going into the base, milliamps coming out of the collector, and we have gain, AC gain through the circuit. These two resistors here, as discussed, set the overall gain of the circuit, the amplification factor. Capacitor here is simply to block the DC element coming out, and capacitor here is to block any DC bias going back to and interfering with the signal generator. We can see on our digital meter here, digital meter is measuring RMS voltage. Oscilloscope screen is measuring at the moment peak to peak values. Okay, so this is, what do we mean by RMS? What we mean by RMS is root mean square. What that tells us is the effective energy value of that AC signal coming out. It is the peak value divided by the square root of 2. So we can get our peak value from the oscilloscope screen, which is 9.5 volts peak to peak. So the peak value is going to be half of that. So that's going to be approximately 4.8 volts coming out. If we divide that by the square root of 2, we get to our RMS voltage of 3.2 volts. It's telling you the effective energy level of that voltage coming out. It's not the average or the mean. The mean of an AC signal is 0 because it has symmetrical positive and negative half cycles. It's the energy content. So if we have a 9.5 volt peak to peak signal, we have an RMS value of that signal as being 3.2 volts. Thank you for watching, and please subscribe.